You know, when I was a young man sitting in Paris, surrounded by the chaos of a world that had just been torn apart by war, I found myself asking the kind of questions that have no comfortable answers. Not political questions, not social ones, but the deepest question a human mind can dare to ask. What is the true nature of reality? And reality, my friends, has a speed limit. Now, I know what some of you are thinking. You have seen science fiction films. You have read stories of starships jumping across galaxies in the blink of an eye. And somewhere in the back of your mind, you have this quiet hope. Maybe, just maybe, the universe will make an exception. Maybe someday we will be clever enough, advanced enough to slip past the boundary that light has drawn across the cosmos. I am here today to tell you, with all the gentleness I can offer, that this hope rests on a misunderstanding, not of technology, not of engineering, but of what matter itself actually is. And this is where my life's work becomes relevant to your question. Let me take you back to 1924. I was a doctoral student, and I proposed something that most of my professors found, let us say, uncomfortably bold. I suggested that if Einstein had shown us that light, which we had always thought of as a wave, could behave like a particle, then perhaps electrons, which we had always thought of as particles, could behave like waves. Every particle of matter, I said, has a wavelength. Every electron, every proton, every atom you are made of right now is simultaneously a particle and a wave. I called this the matter wave, the wave of the pilot. And when the experiment was done, when Davison and Germer in America confirmed that electrons do indeed diffract like waves, the world had to accept something extraordinary. Matter is not what we thought it was. It is not little solid balls of stuff rolling through empty space. It is something far more subtle, far more connected to the fabric of space and time itself. Now, why does this matter for the speed of light? Because to understand the speed limit, you must first understand what moves. When we talk about a particle, say an electron traveling through space, what is actually happening at the deepest level? There is a wave, a probability wave, a pattern of oscillation that carries information about where the particle is likely to be found, what momentum it is likely to have, what energy it carries. The particle and its wave are inseparable. They are, in a profound sense, the same thing. Now, here is where Einstein enters the picture, and here is where I must ask you to follow me with great care, because this is the moment where the universe shows you something genuinely astonishing. Einstein, in 1905, gave us the special theory of relativity. He did not simply say light is fast. He said something far more radical. He said that the speed of light is not a speed in the ordinary sense at all. It is a fundamental constant of nature, a conversion factor between space and time. When you write his famous equation E equals m squared, you are looking at a statement about the geometry of the universe. Mass and energy are two faces of the same coin, and the exchange rate between them is the square of the speed of light. What does this mean for a particle that tries to reach that speed? Think of it this way. When a particle moves, it carries momentum. My equation for matter waves tells us that the wavelength of a particle is equal to Planck's constant divided by its momentum. As the particle moves faster, its momentum increases and its wavelength becomes shorter and shorter. The wave becomes more and more compressed. Now, what happens to the energy of this particle as it accelerates? Einstein showed us that the total energy of a moving particle is not simply 1/2 times its mass times its velocity squared, as Newton would have had it. The true relativistic energy is the rest mass energy plus the kinetic energy of motion. And as the velocity approaches the speed of light, this total energy grows without any upper bound. It does not just get large, it approaches infinity. To push a particle to exactly the speed of light, you would need to give it an infinite amount of energy. And where in the universe would you find infinite energy? Nowhere. Because the universe is finite. Because every star, every galaxy, every quantum of radiation that has ever existed does not add up to infinity. This is not a technological limitation. This is not a problem of having the wrong kind of engine or the wrong kind of fuel. This is mathematics. This is geometry. The speed of light is not a wall that something might one day break through. It is more like the concept of the horizon. You can walk toward it forever and you will never reach it, not because you are slow, but because of what a horizon fundamentally is. But now let me go deeper, because this is where my contribution becomes truly interesting. When I described matter waves, I was thinking about something I called the phase velocity and the group velocity. This distinction is crucial, and I want you to understand it because it is one of the most beautiful and mysterious aspects of quantum mechanics. Imagine you drop a stone into a still pond. You see ripples spreading outward. Now look carefully at one of those ripples. There is the overall shape of the disturbance, the envelope, the hump of water, moving at one speed. But within that hump, you see individual wave fronts, the tiny crests and troughs moving at a different speed. The speed of the envelope is called the group velocity. The speed of the individual wave fronts is called the phase velocity. For a matter wave, the phase velocity, the speed at which the individual wave crests move, can actually exceed the speed of light. I showed this in my original work. The phase velocity of a matter wave is greater than c. For a moment, when I first worked this out, I felt a chill of excitement. Could this be the pathway? Could the phase of a matter wave carry something, information, a signal, a particle, faster than light? No. And the reason why not is one of the most elegant disappointments in all of physics. The phase of a wave carries no information. It carries no energy. It carries no particle. The phase velocity is like the speed at which the pattern of a carpet appears to move when you shake one end. The pattern can ripple along faster than any physical thing, but nothing physical is actually moving at that speed. What carries the particle, what carries the energy, what carries anything real is the group velocity. And the group velocity of a matter wave is exactly equal to the velocity of the particle itself. And the velocity of the particle, as Einstein showed, can never reach c. The universe is so perfectly constructed that the one part of the wave that moves faster than light is precisely the part that carries nothing. No information, no signal, no causal influence. The very thing that might have allowed us to cheat is the one thing that is completely empty of physical content. I remember sitting with this result for a long time, not with disappointment, but with something closer to awe. The laws of physics are not a collection of arbitrary prohibitions. They form a coherent, self-consistent, breathtakingly elegant structure in which every apparent loophole closes itself the moment you look at it carefully. Let us now speak about what this means for mass itself, for you, for me, for every object in the physical world. Einstein's equation for relativistic momentum is not simply mass times velocity. It is mass times velocity divided by the square root of 1 minus v squared over c squared. This denominator, this square root, is the key to everything. When v is small compared to c, the denominator is very close to 1, and we get Newton's old formula back. This is why Newton's physics works perfectly well for cars and airplanes and cannonballs. But as v approaches c, the denominator approaches 0. And when you divide by something that approaches 0, the result approaches infinity. The relativistic momentum of a particle moving at the speed of light would be infinite. The energy required to give it that momentum would be infinite. Now, a massless particle, a photon, a particle of light, can travel at c precisely because it has no rest mass. The formula for a massless particle is different. It does not have a rest energy in the usual sense. Its energy is entirely kinetic, entirely a product of its motion. For a photon, there is no such thing as being at rest. Remove its velocity and you remove its existence. But you and I are not photons. The atoms in your body have mass. The electrons orbiting their nuclei have mass. The quarks inside the protons and neutrons in those nuclei have mass. And because of that mass, you are forever barred from the exclusive club of light speed travel. This is sometimes presented as a sad thing, a limitation, a cosmic prison. I would ask you to consider it differently. It is precisely because massive particles cannot travel at the speed of light that time flows for us. It is precisely because we are bound below c that we experience past and future as distinct things, that cause precedes effect, that memory is possible, that thought is possible, that you are sitting here and I'm speaking to you across time. If a particle could travel at c, it would experience no time at all. From the photon's perspective, if we can speak of such a thing, the moment of its emission and the moment of its absorption are simultaneous. The photon does not travel. It simply exists across the entire path at once. For a photon, there is no journey. There is no experience of space or time. There is only an instantaneous connection between two events. You do not want to be a photon. You want to be a wave particle with mass, moving through time, accumulating experience, asking questions, building theories. And to be that, you must be slower than light. Now let me address the question that always comes up at this point, because I have been in enough lecture halls to know exactly what you are thinking. What about quantum entanglement? When two particles are entangled and you measure one of them, the other one instantaneously, regardless of distance, takes on the corresponding state. Does this not violate the speed of light? Does this not show that something can travel faster than c? This question is one of the most profound in all of modern physics, and it touches directly on the foundations of the theory I helped to build. Let me address it with complete honesty. Yes, the correlations in an entangled system are instantaneous. If you measure the spin of one electron here and find it is pointing up, you instantly know that its entangled partner, even if it is on the other side of the galaxy, will be found to be pointing down when measured. The correlation is real. The instantaneousness is real. This was confirmed by experiments, by the work of Alain Aspect and others, in ways that leave no room for doubt. But and this is the crucial point, you cannot use this correlation to send information faster than light. Why? Because the result of your measurement is random. When you measure the spin of your electron, you do not choose what result you get. The universe chooses. You might get spin up, you might get spin down, with equal probability. Your partner measuring their electron also gets a random result. Neither of you can control your outcome. Neither of you can encode a message in what you observe. Only when you later compare your results through a classical channel, through a phone call or a radio signal that travels at or below the speed of light, do you discover the correlation. The correlation was always there, woven into the quantum state of the entangled pair from the moment of their creation. But the correlation alone, without classical communication, carries no information. The universe, once again, closes the loophole with surgical precision. I want to pause here and say something that goes slightly beyond the physics, because I think it is important. When I developed the theory of matter waves, I was deeply influenced by my philosophical convictions. I still believe, that behind the mathematical formalism of quantum mechanics, there is a real physical picture, that there is something genuinely wave-like about matter, not merely as a computational convenience, but as a description of what is actually there. In my later years, I became associated with what is called the pilot wave interpretation of quantum mechanics. The idea that particles have definite positions and velocities guided by a real wave field that I called the pilot wave. This view was controversial. The mainstream of physics, following Bohr and Heisenberg, took a different path. The Copenhagen interpretation, which is more agnostic about what is really there between measurements. I will not resolve that debate for you today. What I will say is this: regardless of which interpretation you prefer, regardless of what you believe about the ultimate nature of reality at the quantum level, the constraint imposed by the speed of light survives. In pilot wave theory, the wave field itself, the pilot wave, does have instantaneous connections across space. But once again, these connections cannot be used to send information faster than light, for exactly the same reasons as in standard quantum mechanics. The speed limit is not an artifact of any particular interpretation. It is woven into the structure of the theory at every level. So let us come to the end of our journey today, and let me try to leave you with something more than just a collection of prohibitions. The speed of light is not a wall. It is a mirror. When you look at it carefully, it reflects back to you the deepest truths about the nature of space, time, mass, and energy. It tells you that space and time are not separate stages on which events unfold, but a single unified fabric, space-time, and that the geometry of this fabric enforces causality. It tells you that mass and energy are different forms of the same underlying thing. It tells you that information, genuine information, the kind that can be used to influence events, is a physical quantity, subject to the same laws as matter and energy. When I look at the universe through the lens of my matter-wave theory, I see something that continues to fill me with wonder even after decades of study. Every particle around you, every atom in your hand, is simultaneously a localized thing and a spread-out wave. It has both particle-like and wave-like aspects that cannot be separated. And this wave nature is not just a curiosity. It is the reason atoms are stable, the reason chemistry works, the reason there is a world for us to live in at all. The quantization of energy, the discrete spectrum of hydrogen, the stability of matter, all of these emerge from the wave nature of the electron, from the requirement that matter waves fit standing patterns around the nucleus, just as the vibration of a guitar string can only produce certain notes. And the speed of light sits at the center of all of this, not as an arbitrary number, 299,792 is 458 meters per second, but as the fundamental conversion factor that tells you how many meters of space are equivalent to 1 second of time. Change the speed of light and you change the size of atoms. Change the size of atoms and you change chemistry. Change chemistry and there is no life, no planets, no stars, nothing but a formless, structureless void. We are not imprisoned by the speed of light. We are made possible by it. The universe gave you a finite speed for light, and in doing so, it gave you time, causality, chemistry, biology, consciousness, and the ability to sit and wonder why the universe is the way it is. That, my friends, is not a limitation. That is the most extraordinary gift in the cosmos. And I leave you today not with the frustration of a door slammed shut, but with the invitation to look more carefully at the door itself, to ask what it is made of, why it is there, what it tells us about the room we are standing in. The physics is not finished. My matter-wave hypothesis opened a door, and quantum mechanics walked through it and found a universe far stranger and richer than anyone had imagined. There are still deep questions about the nature of the quantum state, about the boundary between quantum and classical, about gravity and quantum mechanics and how they are to be unified. But whatever answers emerge from those explorations, I am quite certain of this. They will not give us faster than light travel. They will give us something better. They will give us a deeper understanding of why the universe is exactly as fast and exactly as slow as it needs to be. Thank you